Assalamualaikum warahmatullahi wabarakatuh. My name is Waskito. In this video, I will talk about the synchronization tools on operating system. Before we talk further, we should know a few points first. Processes can execute concurrently, may be interrupted at any time, partially completing execution. Concurrent access to shared data may result in data inconsistency. Maintaining data consistency requires mechanism to ensure the orderly execution of cooperating data. Concurrent access to shared data. Suppose that two processes A and B have access to a shared variable balance. Process A is balance equal balance minus 100, and the process B is balance equal balance minus 200. Further, assume that process A and process B are executing concurrently in a time-share multi-program system. This situation can cause problem as both processes attempt to change the value of the balance variable concurrently without proper synchronization. This is caused by a rest condition. So what is a rest condition? Rest condition is a condition where the outcome of the program execution depends on an unpredictable execution order. From process A and process B on the previous slide, we have the different scenario that produce the different outcomes. Like we can see on the scenario 1, the balance is decreased by 300, and the scenario 2, the balance is decreased by 100. So we would arrive at this incorrect state because we allowed both process to manipulate the variable balance concurrently. To guard against the race condition on previous slide, we need to ensure that only one process at a time can be manipulating the variable balance. Situations such as the one just described occur frequently in application and operating system as different parts of the system manipulate shared resources. In multi-core systems, an increased emphasis on developing multi-thread applications. In such applications, several threads which are quite possibly sharing data are running in parallel on different processing cores. We require that the process be synchronized in some way. Critical section problems. Section of code that manipulates shared resources. Only one process or thread is allowed to run this section at a time. Consider a system on, of, and processes. Each process has critical section segment of code. Process may be changing the common variables, updating table, writing file, and etc. When one process is critical section, no other may be in its critical section. Critical section problem is to design protocol to solve this. Each process must ask permission to enter critical section in entry section, may allow critical section with exit section, then reminder section. Yeah, as we can see on the screen, this is the general structure of process PI. So what is the intersection? On the intersection, you will checking and preparing before entering the critical section, such as using logs or semaphores to ensure only one process or thread can enter. And then the critical section, a section of code that manipulates shared resources. Only one process or thread is allowed to run this section at a time. And then exit section. Clears or release synchronization resource after exiting the critical section, allowing another process or thread to enter. And then the reminder section is the section of the code after exiting the critical section, usually operation that do not require special synchronization. Yeah. To solve the critical section problem, we have three basic principles in the synchronization problem of concurrent programming. The first one is mutual exclusion. If process P is executing in its critical section, then no other processes can be executing in their critical section. And then the progress, if the process is executing in its critical section and there exist some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. And then the last is bounded waiting. A bound must exist on the number of times that other processes are allowed to enter the critical section after a process has made a request to enter its critical section and before that request is granted. Okay, the critical section handling in operating system to a process depending on if kernel is preemptive or non-preemptive. Preemptive is allows preemption of process when running in kernel mode, and non-preemptive is runs until exit kernel mode blocks or voluntarily yield CPU. Here we talk about the Peterson solution, not guaranteed to work on modern architecture, but not good algorithmic description of solving the problem. The Peterson solution just can be applied to process solution. Assume that the load and store machine language instruction are atomic, that is, cannot be interrupted. The two processes are two variables. The variable turn indicates whose turn it is to enter the critical section. The flag array is used to indicate if a process is ready to enter the critical section. Flag I equal true implies that process P1 is ready. And this one is the algorithm for process PI. Okay, so on the Peterson solution, provable that the three uh, critical section requirements are met. The first one is mutual exclusion is preserved, and then the progress requirement is satisfied, and bounded waiting requirement is made. Okay, also useful for demonstrating an algorithm. Peterson's solution is not guaranteed to work on modern architecture. Understanding why it will not work is also used for better understanding race condition to improve performance. Processor and or compilers may reorder operations that have no dependencies. For single thread, this is okay as the result will always be the same. For multi-thread, the reordering may produce the inconsistent or unexpected results. Two threads share the data, and then the thread 1 performs, thread 2 performs. What is expected output? Okay, the 100 is the expected output. However, the operation for thread 2 may be reordered. If this occurs, the output may be 0. The effect of instruction reordering in a partition solution. This allows both processes to be in their critical action at the same time. Okay, the next one we will talk about the synchronization hardware. Many systems provide hardware support for implementing the critical section code. Uniprocessors could disable interrupts. We will look three forms of hardware support. The first one is memory barriers, and then hardware instruction, and then the third one is atomic variables. Memory barriers. Memory model as the memory guarantees a computer architecture makes to application programs. Memory models may be either strong or other, where a memory modification of one processor is immediately visible to all other processors. Weakly order, where a memory modification of one processor may not be immediately visible to all other processors. A memory barrier is an instruction that forces any change in memory to be propagated, made visible to all other processors. Okay, we could add a memory barrier to the following instruction to ensure thread 1 output 100. Thread 1 performs like this, and the thread 2 performs is like this. Okay, and then the second one of the hardware support is hardware instruction. Special hardware instruction that allow us to either test and modify the content of a word or to swap the content of two words automatically. Test and set instruction and compare and swap instruction. Okay, the first we will talk about the test and set instruction. The main function of the test and set instruction is to set the value of a variable to a specific value, usually 1, and automatically restore the previous value. So the test and set instruction execute automatically, return the original value of base parameters, and set the new value of base parameters to true. And the solution using test and set the Boolean variable log initial to false. Okay, and then compare and swap instruction. The main function of the compares the value of a memory location with the expected value. If the value is equal to the expected value, then it is replaced with a new value. Okay, this is the syntax of the compare and swap instruction. So the compare and swap instruction execute automatically, return the original value of base parameter value, set the variable value, the value of the base parameter new underscore value, but only if a value is equal the expected is true. That swap take place only under this condition. Okay, the last one is atomic variables. Typically, instructions such as compare and swap are used as building blocks for other synchronization tools. One tool is an atomic variable that provides atomic uninterruptible update on basic data types such as integers and booleans. For example, the increment operation on the atomic variable sequence ensure sequence is incremented without interruption. Okay, the implementation of increment function, you can follow like this. Okay, the mutex logs previous solution are complicated and generally inaccessible to application programmers. Operating system designer build software tools to solve critical section problem. Simplest is mutex lock. Protect a critical section by first accrue and lock them, release, then lock. Boolean variable indicating if lock is available or not. Calls to acquire and release must be atomic, usually implemented via hardware atomic instructions such as compare and swap. But this solution requires busy waiting. What is busy waiting? This lock, therefore called spin lock, because the process spins while waiting the lock become available. Okay, this is the solution to critical section problem using lock. The mutex locks definition. These two functions must be implemented automatically. For test and set and compare and swap can be used to implement this function. And then we have Smapper, synchronization tools that provides more sophisticated ways than mutex lock for process to synchronize their activities. Smapper we call as is integer variable can only be accessed via two invisible atomic operations, wait and signal, originally called P and V. The definition of wait operation is like this, and the signal operation is like this. Okay, smapper usage. Counting smapper integer value can range over an unrestricted domain. Binary smapper integer value can range only between 0 and 1. Can solve various synchronization problems. Counting smappers can be used to control access to a given resource consisting of a finite number of instances. Each process that wishes to use a resource perform a wait operation on the smapper, thereby decrementing the count. When a process releases a resource, it performs a signal operation, incrementing the count. When the count for the smapper goes to 0, all resources are being used. After that, the processes that wish to use a resource will block until the count becomes greater than 0. Okay. Smapper implementing with no basic waiting. With each smapper, there is an associated waiting QE. Each entry in a waiting QE has two data items. Value, the data type is integer, and the pointer the next record is the list. Two operations, block, place, the process invoking the operation on the appropriate waiting QE, wake up, remove one of processes in the waiting QE and place it in the ready queue. So this is the algorithm of wait and signal. Okay, the next one is monitors. It's high-level abstraction that provides a convenient and effective mechanism for process synchronization. Abstract data type internal variable only accessible by code within the procedure. Only one process may be active within a monitor at a time. Pseudocode syntax of a monitor. This is the systematic view of a monitor. The other condition variables, condition x and y. Two operations are allowed on a condition variable x wait. A process that invokes the operation is suspended until another process invokes x signal. A signal resumes exactly one of processes, if any, that invoke x wait. If no x wait on the variable, then it has no effect to the variable on the variable. Okay, and then liveness, deadlock. Two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. Let S and be too small for initialize to 1. Consider if P0 execute wait S and P0 wait key. When P0 execute wait key, it must wait until P1 execute signal Q. However, P1 is waiting until P0 execute signal S. Liveness. The other forms of deadlocks, starvation, indefinitely blocking. A process may never be removed from the small queue in which is suspended. Priority inversion scheduling problem when lower priority process hold a look needed by higher priority process. Solve of higher priority inheritance protocol. Example, let T1, T2, and T3 be the three periodic tasks with decreasing order of priorities. Let T and T3 share resources as. The priority inheritance protocol solves the problem of priority inversion. Under this protocol, if a higher priority task TH is blocked by a lower priority task T1 because tiled TL is currently executing critical section need by TL temporarily inherits the priority of TH. When blocking changes, for example, is TL exits the critical section, TL resumes its original priority. Unfortunately, priority inheritance may be lead to deadlock. Okay, for the summary is a risk collision occurs when processes have concurrent access to shared data and the final result depends on the particular order in which concurrent accesses occur. Risk condition can result in corrupted values of shared data. A critical section is a section of code where shared data may be manipulated and a possible race condition may occur. The critical section problem is to design a protocol whereby processes can synchronize their activity to cooperatively share data. A solution to the critical section problem must satisfy the following three requirements. The first is mutual exclusion. The second is progress, and the third is bound waiting. Mutual exclusion ensures that only one process at a time is active in its critical section. Progress ensures that program will cooperatively determine what process will next enter each critical sections, and the bounded waiting limits how much time a program will wait before it can either enter its critical section. Okay, and then the software solution to the critical section problem, such as Peterson solution, do not work well on modern computer architectures. Hardware support for the critical section problems includes memory barriers, hardware instructions such as the compare and swap instruction, and atomic variables. Okay, I think it's enough for me. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.